going to be on a new model specification for geothermal ground source heating and cooling system piping, the piping that goes in the ground. And there's reasons why we need a presentation on this. So we'll be talking about how to write a good, or even how to copy language to make a good geothermal piping spec. Quick introduction, this is me up here. My name is Lance. I work for the Plastics Pipe Institute, which is a nonprofit trade association. That started way back in 1950. Yes, it was plastic pipes way back in 1950. And after a few years of production, some independent engineers thought, you know what, we should work with the other plastic pipe manufacturers and write some standards. Let's standardize our dimensions and our materials and the ways of joining these pipes and designing fittings. So that was kind of the need behind the beginning of the Plastics Pipe Institute. That was 75 years ago now. So the group still kind of does a lot of the same stuff today. PPI is made up of about 200 member companies involved with plastic piping in North America that pay dues to belong to the association. It's a nonprofit, and we do research, education, technical publications, and a lot of codes and standards work and things like that. So I started out in the plastic pipe industry way back in 1993, which doesn't feel like that long ago, but to my kids that was like dinosaur days, according to them. So it's a dynamic industry, and there's a lot more science and details involved with plastic piping than you could ever imagine. So my job is to make it feel exciting. Within PPI, our organization, we have 5 different divisions. If you go to our website, we've got a lot of free information there about plastic piping. So PPI does not make anything. We don't sell anything. We develop information and put it out there in the public space for free. So we're meant to be a public resource for information and standards and guides and manuals and things like this. If you go to our website and you're looking for information related to any of these materials, plumbing and mechanical pressure pipe materials, just go to plasticpipe.org/building construction. That's the name of the division that represents all these types of materials. This is like a family picture here for the different types of materials we represent, the pressure pipes used in plumbing and mechanical systems. Or even better, follow us on LinkedIn if you're connected with that. So what we're going to be talking about today is a new model specification that our organization published for the first time in 2023. We've been publishing model specifications for use by engineers and specifiers for years now. So this was the 7th model specification that we published. That's why it's called PPI MS7. But this one is focused on plastic piping materials used in ground source geothermal systems. And we're going to be talking about why this is important, talking about how to use it. But first, we're going to be talking about the codes and standards related to geothermal piping in North America. And mostly what we're going to be focusing on are these 4 different materials here. Now, when we look at the ground loop piping, the piping that's buried in the ground for heat exchange with the earth, 99.2% of the time it's HDPE. So that's what we're going to be talking about most of the time. There's 2 other materials, though, that are also allowed to be used as ground loop piping. And these are more expensive, higher grade, higher performance materials. Most of the time we don't need that higher performance, like higher temperature capability. But those other materials are known as polyethylene of raised temperature resistance, or PERT, or cross-linked polyethylene, or PEX. So those are the 3 materials that we'll be talking about that you can use for ground loop piping. They are very similar to each other in how they work and feel. And then polypropylene, which is a rigid plastic pipe material that's often used for indoor piping, like big manifolds and mechanical rooms and things like that. So that's what we'll be talking about here today, is a bit of an introduction. And then terminology-wise, if I say geothermal, I'm not talking about, 1,200-foot deep holes where we're tapping into hot steam in Reno, Nevada to get hot steam out of the earth. We're talking about geo-exchange, or heat exchange with the earth, also known as ground source heat pump systems or geo-exchange systems. So here's the outline of the presentation. First, we're going to focus on HDPE, which means high-density polyethylene. That's by far the predominant material used for these ground loop piping systems. We're going to talk about the pipe and how it's approved in codes. So we're going to take a look at some codes and how codes approve polyethylene and tell you what kind of polyethylene you can use. And then we're going to talk about product standards from organizations such as ASTM, AWWA, CSA, and NSF. So we're going to geek out a little bit in that part, talking about what the standards actually mean, all those numbers and things like that. And then we're going to take a look at some inappropriate specifications that have really been published for big commercial jobs, where the engineer did his or her best job to put together a generic specification that would include multiple materials, but copied and pasted from different things and ended up writing a specification that was just not right at all. So we'll give some examples there. That's kind of identifying here's the problem, and then the solution for the problem is just go to the PPI document, MS7, and copy and paste the sections from there. So we make it easy to actually write a good model specification without a lot of research, just copy and paste from that industry document. So that's our outline, and like I said, we're going to focus on HDPE for the most part here, and we're going to start by talking about codes. And I'm pretty sure everybody in this room here knows what a code is, or you've interacted with codes and things like that. A code, technically, it's a legally adopted document by jurisdiction, like the state of Florida or the city of LA or something like that, for the purpose of regulating a portion of the design and construction industry. So it's a pretty wide umbrella because we have electrical codes, plumbing codes, mechanical codes, building codes. There's lots of codes out there. But hopefully you're also familiar with the term model code, because most of these organizations don't have the time or the capability to actually start from scratch and create their whole new building code. I mean, do we really need a building code for the city of Orlando when we could just use a bigger building code that already exists, that's been developed over the last 40 years by other people? So most of the time, cities, counties, states, they adopt something called a model code, which has been written by groups that are focused just on publishing codes. Model codes come from so-called code development bodies or code agencies. And the examples of these model code developers are groups like CSA up in Canada. In the United States, we have International Code Council, that's ICC. We have a group called IAPMO, which stands for the International Association of Plumbing and Mechanical Officials. And also, back in Canada again, we have the group NRC, which is the National Research Council up in Ottawa, Canada. So different groups out there write these so-called model codes, and then these model codes get adopted by different jurisdictions, and then they become the law of the land. And by the way, it might get a little confusing because at some point today we're going to be talking about a CSA standard called C448, which is actually adopted as the code across Canada, the code for geothermal systems. So sometimes a standard, once it gets adopted into legislation, then it becomes a code. So in the United States, though, and across Canada, here are the 4 major codes that are published that have something to do with geothermal systems. So in Canada, the code comes from CSA. It's known as ANSI CSA IGSHPA. So it's actually kind of published by these 3 organizations, C448. And that's been around for a long time in Canada. The latest version is 2016. There's a new version coming out later this year of C448. In the United States, then, we have our 2 major code developers, ICC and IAPMO, and they publish the International Mechanical Code, the Uniform Mechanical Code, and then another code from IAPMO called the Uniform Solar Hydronics and Geothermal Code, which focuses on solar, hydronics, and geothermal systems. Hey, guys. And these codes are updated every few years, literally, on 3-year code cycles. So the latest edition of those codes is the 2024 code year. They were all published last year. So we're going to take a look in some of those codes and see how do they actually refer to geothermal piping, because this is important when you're writing specifications. You want to make sure your specifications comply with the codes, right? So first we're going to take a look at the CSA code. Is anybody here from Canada? Some Canadians? Okay, wonderful. So CSA C448 is the law of the land in Canada. I was born in Canada, so I'm a dual citizen, but yeah, originally from PEI. So in the CSA standard, here's the section on polyethylene piping, if you can read this. And basically what it says is polyethylene pipe and tubing shall comply with one of these standards. We're going to talk about standards in a few minutes. But the code doesn't tell you the dimensions of the pipe or the pressure rating of the pipe or how tightly the pipe can be bent and things like that. The code basically tells you refer to a standard. As long as the pipe meets that standard, then it's okay by us to use it for this application. So that's how the CSA code refers to pipe. And then it gets into more details down below a little bit in terms of the minimum material grade can be used and things like that in case the standards have a lot of flexibility. In the International Mechanical Code, which I think is the law of the land here in Florida, in Chapter 12 of that code, they have a section on ground loop piping. They call it ground source loop pipe. And if you look at that table, where it refers to high-density polyethylene, again, it refers to standards. The same standards that we just saw in the CSA code. And then there's a separate table in the IMC that refers to the fittings that you can use with geothermal pipe. So this is a different table than the one I had on the screen a second ago. It looks the same, it's organized the same, but in this case, if you're using high-density polyethylene pipe, and these are the other pipes that this code allows you to use for ground loop piping, by the way, but for polyethylene, it says the fittings must meet one of these standards. So they're referring to standards. And then if we look at the IAPMO codes, here's the Uniform Mechanical Code. Chapter 17 of the latest version of the UMC is all about geothermal ground loop systems. And it has a table focused on ground loop piping, or plastic ground source loop piping, they call it. Again, for polyethylene, here's polyethylene in the table. Only these 4 materials are approved according to this code for ground loop piping, which is good. That's what we recommend. And here are the standards that they refer to. In that case, the UMC also has a table for fittings. This is going to feel a little bit repetitive, but the 2 different organizations are treating geothermal ground loop piping in a very similar way. The point here is they refer to product standards. They don't tell you exactly what dimension to use or what pressure rating to use or anything like that. They refer you to a standard and say, basically, as long as it meets one of these standards, then it's approved by us. But those standards still have details that we'll talk about in a second. Here's the other code that we want to point out. Not everybody knows this one exists. It's called the Uniform Solar Hydronics and Geothermal Code. This used to be known just as the Uniform Solar Code a long time ago. Starting in 2015, hydronics was added into the code, and then starting in the 2018 edition of this code, there was a whole new chapter in geothermal systems added to the code. My friend at the front here, P.Eng, and I get involved with these IAPMO codes, developing these codes. So regular people can get involved with development of these codes. And that's how it refers to ground loop piping. So I know this is kind of getting into the weeds right up front here, but the point we're trying to make is when it comes to approvals for what kind of pipe is allowed to be used in a certain area, first you have to check with the code, right? You have to find out, is there even a code that applies to geothermal in my jurisdiction? In some cases, like if you go to Minnesota, they do have a Minnesota state code for geothermal systems. It's not that great. It's kind of old, it needs to be updated, so people within industry are trying to work with them on things like that. It would be better if Minnesota would just adopt one of these existing model codes so that we'd have more harmony across the country. Because the problem is, if you're a geothermal installer or designer working in multiple states, the law of the land in one state might not be the same as the law of the land in the state next door. So inconsistency can be a bit of a problem. Yeah, Pete?
Is there a list of who does and who don't?
Kind of. Like if you go to the ICC website, you can actually find out what states adopt their codes. But even on their map, it looks like most of the country adopts IC codes. It's not necessarily, it could be just one county within a state adopts one of their codes, and they'll say this state uses our code, but it's not necessarily the whole state. So at a really granular level, there's no list out there. You almost have to start making phone calls and find out on a county by county basis, what's the law of the land if I move to the next county? Yeah, it's a bit awkward. Canada, it's a bit similar. There's one national building code for Canada, and one CSA standard for Canada for geothermal. All right, so we talked about standards a lot because the codes refer to standards. Now let me give you a little bit of an insight into these standards. I am an official pipe nerd, okay? An official pipe geek, and I wear that title. Well, because I get involved with the development of these standards. Anybody from the industry, anybody from the public can join groups like ASTM or CSA and get involved with the development of the standards. You don't have to pass a test, you don't have to be an engineer, you don't have to work for a pipe company to get involved with developments of standards. So when I go through this stuff, if you think, wow, that's interesting, I'd like to get involved, or if you think, wow, that standard is terrible, I'd like to fix it, anybody in this room could apply and become one of these organizations and get involved with that if you so wanted to. So the standards, they come from these so-called standards development organizations, SDOs, a new acronym here today. And some examples of SDOs are shown here. AHRI, that's Heating Refrigeration Institute, right? ASHRAE, hopefully we know what ASHRAE means because we're at their conference. AWWA is the American Waterworks Association. ASTM used to be known as the American Society for Testing and Materials. It's more than 125 years old. CSA is the Canadian Standards Association. IATLO and ICC, I already mentioned those guys. NSF used to stand for National Sanitation Foundation, potable water type standards, but now they do lots of standards for other things, so there's not just potable water. So now they're just known as NSF. And for a group to actually have the authority to write a standard, believe it or not, they actually have to be accredited in their country. So if you're thinking, why can't I just develop my own standards organization and I'll write it the way I want it to be? If you're in the United States, first you'd have to get accredited by the American National Standards Institute, or USA, that's for USA, ANSI. And in Canada, you'd have to be accredited by Standards Council Canada, which is a quasi-governmental thing up in Canada. So these are the groups that are officially authorized to develop standards for all kinds of products in those two respective countries. There's a lot of rules here. Piping manufacturers have to follow a lot of rules. Specifiers have to follow a lot of rules as well, right? So when we then get involved in standards, obviously standards have some purpose. The purpose of the standard is up here, and at least for piping, the purpose of the standard is to specify minimum requirements, not maximum or not as like a best practices, how I do it kind of guide, but it's to specify the minimum requirements for product design, manufacturing, testing, and certification. So those are four important kind of purposes of the standards. Why do standards exist? Obviously to protect consumers. So if we're talking about geothermal systems, imagine all these houses here had geothermal systems, or even if only 1 out of 10 had geothermal systems, you would want there to be some sort of standard so that the pipe that goes in the ground is going to last for a very long time. And the water goes through the pipe. And everything else involved with our construction has standards for it. There's standards for shingles and plywood and OSB and concrete and nails. There's standards for pipe as well. So it's important to have the standards out there. And then the manufacturers, the people that are making the pipe, their job is to know what the standards are and to make sure their pipe complies with the standards. So when we get involved with geothermal piping, and specifically high-density polyethylene piping, when we looked at the codes a few minutes ago, here were all the different standards that were listed in those codes. So ASTM D2737, the top one in the list, it actually has a name. And you could actually just go to Google and type in ASTM D2737, and it'll bring you up an ASTM webpage that tells you the content of that standard in terms of big picture. Here's what the standard is about. Here's why it exists. To actually get a copy of these standards organizations, their business is developing and selling the standards. So if you actually wanted a full copy of D2737, all you have to do is provide a credit card number, and they will sell you a PDF copy of that standard. It's open to anybody with a credit card. And then you can buy your own copy of D2737 and D3035 and F714. Or if you join the organization, then you get a lot of those standards for free as part of your annual organizational dues, which is actually cheaper than buying 3 of the standards. You might as well just become a member, and then you get a whole bunch of them for free. Hot tip. But there's a lot of the standards that we actually talked about in the HDPE pipe business. Those are the standards for pipe and tubing. And then here's all the different standards for the fittings, because for polyethylene fittings, there's also standards for those. And then there's also standards for how you join the fittings to the pipe or tubing. And those joining standards are right here. And then when it comes to protection of drinking water safety, like if you're putting pipe in an aquifer, drilling down through the ground, and the plastic pipe is passing through an aquifer, well, that's somebody's drinking water probably. You don't want the pipe to somehow contaminate the drinking water. So it's generally recommended that the pipe that's going in the ground actually be tested and certified to be safe for drinking water, and that way it's not actually contaminating somebody's drinking water. So that's listed there too. Now, so I talked a few minutes ago where these standards come from, and I said they come from standards development organizations. If you look at an organization like ASTM, I think they probably have 30,000 members. Well, nobody is an expert in roofing nails and shingles and OSB and pipe. So they have multiple committees. So they have a pipe that focuses just on plastic pipe, or a committee that focuses just on plastic piping. And that committee is called F17. So if you're a piping guy, you're interested in piping, you would join ASTM and you would check the box and say, I want to be part of this plastic piping committee, which happens to be called F17. And there's about 750 people that are part of that committee at ASTM. People that are involved in the plastic pipe industry, one way or another, and get together to write these standards and revise the standards. And most of them are voting members, which means if anybody tries to change a standard, all these people get to vote on it. And it doesn't get approved, changes don't get approved unless everybody agrees that yes, this change makes sense and is the right thing to do. And if you're ever wondering which committee within ASTM controls an individual standard, what I'm showing here, this little box here is the footnote, the fine print from one of our pipe standards called D3035. And right down at the bottom, it says exactly which committee and even which subcommittee is responsible for this standard. And it tells you what version you're looking at and when it was published. And it even tells you this was originally published way back in 1972. So this standard first came out in 1972, but they get revised sometimes once or twice a year if there's things changing and people need to make changes to these standards. So that's a lot of detail here. Stepping back out, bigger picture, when we look at all the different piping standards, then here's what they actually look like. So this is the AWWA standard for polyethylene water pipe, which some people refer to that standard for the geothermal piping, because if it can hold water pressure, that's what we need our geothermal piping to do as well, is hold water pressure inside. Here's the top part of one of the ASTM standards, D2737. If you can read it, this is for PE tubing. And then the next standard that's going to come up is for PE pipe. There's actually a difference between tubing and pipe, and it has to do with the dimensions. And I have a slide on that coming up soon. So a pipe and a tube are not necessarily the same thing because they actually have different dimensions. So I know we're geeking out here, right? When it comes to this kinds of stuff. Here is the CSA standard for polyethylene pipe. It's called B137.1. Here is one of the NSF standards. There's an NSF standard for polyethylene geothermal pipe called 358-1. And then this is what the NSF standard for drinking water system components looks like. All your potable water pipes and fittings and valves and everything else have to be tested and certified to NSF 61 to make sure that those devices are not going to contaminate your drinking water in any way. So there's standards for everything out there behind the scenes that you probably didn't know about. Maybe you did, but hopefully you feel a little better thinking, nice to know there's a committee out there focused on these standards, protecting us all. To give you an idea of what you'd find in one of these ASTM standards, here's a close-up view of the D3035 standard for polyethylene pipe. That's just kind of like page one. It tells you the scope. Here's what the standard is for. If you read it a little deeper, if you can read this in the back, there's a table here that actually gives you the precise outside diameters for all these different pipes. Here's the exact outside diameter with tolerances. If you can't read this, some of these tolerances are plus or minus 4/1000ths of an inch or 5/1000ths of an inch. 4/1000ths of an inch is the thickness of a piece of paper. So the tolerances and outside diameter for these pipes is really, really small. It's hard to make good quality pipe that meets the requirements because the standards have been refined so much over the years. And then here's another table here that tells you the wall thickness for the pipes for different wall types. So if you've ever heard of SDR21 versus DR17 or DR15.5, in this table here it tells you all the different wall thickness requirements, whether you need a thin wall pipe for low pressure or a thick wall pipe for higher pressure. That's dictated in the standards. There's another part of the standard that tells you the exact material properties for the type of polyethylene you're going to need. That's an eye test. And there's even a section in the standard that tells you exactly what the markings shall be. The minimum requirements. These are all minimum requirements. But even for the markings, it tells you exactly you must have the manufacturer's name there, and a footage mark, and the standard number, and the pressure rating, and some other things. And then some manufacturers go above and beyond that and put the exact date and production codes and other things on their pipes. So there's a lot of detail that goes in these standards. Here's the NSF's 358-1 standard, which is also important because it was written specifically for PE geothermal pipe. So why is there a separate NSF standard for PE geothermal pipe when we already have an ASTM standard for PE pipe? It's because this one has some extra requirements to make sure the pipe is proven to be suitable for ground loop piping. Here's just kind of the scope of that NSF standard. As you can see here, the NSF standard talks about material types and things like that. But one of the most important parts of the NSF standard is the chemical resistance test. And I know this is hard to read in the back, but it basically says you have to test the pipe or fitting material with different glycol materials, different glycol types, to make sure that being immersed in the glycol will not hurt the material in any way. I mean, if you're buying a bucket of glycol, it's probably coming in a polyethylene barrel. So we've known for years and years and years that polyethylene is resistant to glycol and methanol and things like this. But now there's a test to prove it. If it's a pressure pipe going in the ground, they actually do some specific tests to make sure that that pipe will not be affected by the glycol in any way. So the reason I'm showing you this standard is, if a pipe manufacturer says, my pipe is also certified to NSF 358-1, that's a good thing. It means that they're really focused on the geothermal industry and they've done that extra certification. If they haven't done it, then you might want to ask them, how come your pipe is not certified to 358-1? Now, getting into the science of the material, I don't want to spend a ton of time on that, but if you've ever heard of material designation codes, like let me jump ahead over here. If you ever heard of people talking about polyethylene, calling it PE 3408 or 3608 or PE 4710, those digits all refer to specific requirements of the pipe material. And I've organized those requirements in a table here. This is my table, this is not directly out of a standard. And basically, in the 3408, the 3 refers to density. In PE 4710, the 4, the first digit also refers to density. 4 is bigger than 3, so that's probably better. There's other parts of that code that are dictated in the so-called pipe classifications and material designation codes. There's also a 6-digit way, the actual pipe cell classification code that has the full 6 digits, which refers to all of these numbers. So you can actually have a pipe that was called a 345444. That's actually a material grade for a type of polyethylene that we don't really use for geothermal pipe much anymore because it's been kind of supplanted, what's the word I'm looking for here? Obsoleted, yes, by the newer grades of materials. So without getting into the weeds too much, if I back up one slide, if you really want to know exactly what does the 3 and the 4 and the 08 mean, or the 4 and the 7 and the 10 mean in these PE codes, it's actually all dictated in a different ASTM standard, which you can buy for a low price of, I don't know, $50 or something. But it's called D3350, and it has a table that tells you exactly what each of these classifications mean, and what a 4 means versus a 3, or a 5 versus a 4, or a 3, and things like that. So it's actually all written down somewhere, exactly what those digits mean. And in almost every case, a higher digit, a 4 versus a 3, is better. It means improved properties, higher strength, or better resistance to something. The reason we're showing you this is because there has been a big evolution in pipe grade materials over the last 20 years. 20 years ago, almost all the geothermal pipe in North America was called PE 3408. And that was state-of-the-art 20 years ago. And it was a good material. It was coilable, flexible, had pretty good abrasion resistance. It was resistant to glycol and temperature, pressure, things like that. But it did have one big drawback, which mostly showed up in the gas industry, but also showed up in the water and geothermal industry a bit too. And that big drawback was called resistance to slow crack growth. So imagine you're installing pipe in the ground and it gets pulled over a bit of a rock or a sharp edge and makes a bit of a gouge or a scratch in the pipe. Well, that's thinning the wall of the pipe down to one specific location, right? But yet the pressure inside the pipe is the same everywhere. Well, if you thin the wall of the pipe down at one place, and let's say you've gouged out 10% of the wall thickness, that means there's extra stress concentration at that point where there's less pipe wall to resist the pressure. With the old 3408 material, once you had a localized stress point like that, the crack could grow over time, and you would get what's called slow crack growth. Slowly, the crack would grow over years, and eventually you'd get a tear in the pipe, and obviously a pipe failure. So the polyethylene pipe companies that made the materials did lots of research work to find out how to make better polyethylene that wouldn't suffer that problem. And they did that by coming up with materials that they call bimodal resin, which have a mixture of short and long molecules mixed together. so you can have higher density per cubic inch or per cubic millimeter, whatever like that. And then they assigned a test to it, a way of actually testing the resistance to slow crack growth. They come up with an ASTM test for that. And then that gave manufacturers ways of testing and evaluating their pipe to see if their new version of their pipe was better than the old version in terms of resistance to slow crack growth. And so that's one of the properties that's described in this material designation code. So from 3408 to 3608, 3608 was better than 3408 in terms of resistance to slow crack growth. It was a little bit better, but then when they came up with the new so-called bimodal resins, PE4710, it was better in every way. Higher tensile strength, which means better pressure resistance, higher density, again, better strength, and much better resistance to slow crack growth. To give you an example, the old pipe 3408 would last about 50 hours in the test that they would do to evaluate this. The new pipes have to last at least 500 hours, which is 10 times longer, so at least 10 times better. But most of the pipes that are on the market today will actually last at least 2,500 times, which means, whatever that is, 200 times better than the old graded pipe. So it's essentially eliminated the chance of slow crack growth. So 4710 is the current state of the art. It's been around for at least a dozen years now. And almost everybody selling a geothermal pipe today should be making it out of a PE4710 material. And as a specifier, which is the point that we're here for today, you should be specifying PE4710 material because that is the best you can get today. And almost everybody has it. So again, here's a comparison. 4710, higher slow crack growth resistance, higher density, higher stiffness, changes the digits in the code here, and a higher hydrostatic design stress. And this would be marked right in the pipe. This is a close-up of the pipe. It says PE4710. It also has that big class code, the pressure class of 200 psi, and this one happens to be certified to the AWWAC 901 standard. So a lot of this information is actually found right on the pipe. So that was a deep dive into the weeds of pipe standards. I know it's the worst time to do this in the day is right after lunch, and I know this room is really hot and everything else. So thank you for staying awake through all of that part. It is going to get a little more interesting coming up next, trust me. But does anybody have any questions about standards before I move on to the specification part? Yes?
Do you find folks specifying the 4710 for the whole and 3408 or something else on the horizontal assemblies?
Good point. Theoretically, they could do that because if you can control the trench backfill, nice clean soil going backfill against the horizontal pipe, you wouldn't necessarily need the 4710 pipe grade for that. But for the most part, nobody even makes 3408 anymore. So our recommendation is to specify 4710 for everything, and you can allow a thinner wall pipe for the horizontal pipes. They don't need necessarily as thick a wall to resist any kinds of mechanical, nicks and dings they're going to get and things like that. So yeah, thank you. All right, the next part here is hopefully going to be a little bit fun. This is where we're going to give some examples of inappropriate or out-of-date piping specifications. And if you've been following along through all of this, when I show you these specifications, you're going to say, oh yeah, I see what's wrong with that, because I've just taught you all about codes and standards and material grades and designation codes. So we'll be able to pick out these flaws together. The reason, though, that these are a problem, like why shouldn't I be using my specification from 1999, worked well back then, it should still work today, there's actually some good reasons. Because if you write a bad spec, let's say as a specifier, I read what one company said for their spec, and another company said for their spec, and another company here, and I'm just going to try to merge them all together. So I create a super spec that will include everybody's product so that the contractor has 3 approved equals to pick from. I might be creating something that doesn't actually work. I might actually write a type of specification that doesn't even exist. Or it might be incomplete, or just unclear in some way that the people trying to supply pipe for this project are like, I have no idea what the spec is actually looking for, so I'll just supply my cheapest pipe in that case. Somebody could do that, right, if you're not really tight on your specification language. So the wrong products can get installed in that case. If it's an old spec, a specifying product that doesn't even exist anymore, then everybody's kind of guessing. And somebody might say, well, if I can still supply 3408 because that's allowed in the spec, maybe I can find some sitting in a warehouse somewhere. It's been in a warehouse for 20 years, but if that's all they need, I can save a lot of money if I use some old pipe sitting around. That's not good. And like I said, when people are doing these so-called custom specs, a little bit of this, a little bit of that, sometimes we call those Frankenstein specifications. You remember the story of Dr. Frankenstein and the monster he created? He went and took body parts, right? The strongest arms from the guy who had the strongest arms in town, and the strongest legs from somebody else, and the biggest brain who's somebody who used to be the smartest guy in town. And that's how he built Frankenstein's monster, I think, was the best. He was trying to be the best of all these individual parts. It didn't work out very well. So basically he created a monster. And that's sometimes what happens when engineers write their own specifications. So here's some examples of specifications that have little flaws in them that can leave people guessing. On this, and these are real specifications, just kind of scanned. In this example 1 here, geothermal ground loop piping, part 1, general, right at the very beginning. One of the ASTM standards they're referring to is called D2513, if you can read that. That's the ASTM standard for gas pipe. Most of our underground gas pipe is running at about 5 psi. And gas pipes can use a much lower grade of resin than we use for water pipes, which are 100 psi or more. So if they're allowing D2513 pipe, they could get a bunch of yellow gas pipe showing up at the job, which is a really low pressure rated pipe. So obviously that's a flaw. That's not a good idea. Another part of the specification, if we read down a little bit more, and I've highlighted the things that really stand out as a bit of a flaw, it says all components shall be supplied by one manufacturer. Well, to tell you the truth, the guys that make pipes don't make fittings, and the guys that make fittings don't make pipes. So you can get them all from one distributor, but you're really not going to get them all from one manufacturer. So that's not a very helpful thing to write there, unless you want to force the pipe company to go buy a fitting company, so we can put the same name on all of them. And then letter D says, pipe and fitting shall be IGSHPA approved. Greg Kurtz, you work with IGSHPA. Does IGSHPA have a certification program for pipes and fittings? No. IGSHPA doesn't certify or approve pipes and fittings. You're not going out and visiting the factories and doing quality control checks, are you? No, exactly. So there is no IGSHPA approved pipes and fittings. So that's just not helpful. In another part of the specification, it says the acceptable manufacturer. There's only one. It's called Oil Creek Plastics. That is a real company in Titusville, Pennsylvania, where they first actually drilled the very first oil well in America and leaked into the creek. So that's why they call it Oil Creek down there. But if you can read the details of the pipe, it's saying the ground loop heat exchange pipe shall be SDR11, PE4710. We know what that means. High density cross-linked polyethylene, which is PEX. How can it be PE4710 and PEX at the same time? And a very specific type of PEX known as PEX-A. And all these standards listed here are PEX standards from Canada, the US, and Germany. And the Euro symbol is in there for some reason, with the German standards. So again, and by the way, Oil Creek Plastics does not produce PEX. So they're specifying it must be PEX from this company that doesn't actually make PEX. So again, not very helpful. Further on in the same specification, it says, now here it says it shall be SDR 13.5 PE4710 geothermal pipe by Oil Creek Plastics. Now that is actually legitimate. It really can be that. But then down below, when we're looking at the fitting requirements, it says, so up here it's PE4710, HDPE pipe up here, but the fittings must be PEX fittings down below. And then the electrofusion fittings, if you're using those, must be made from PEX for joining to PEX. So again, it's a mishmash, right? This is a Frankenstein spec. They're asking for a pipe from a company that doesn't make that kind of pipe to be used with fittings that don't work with that kind of pipe. Here's example number 2. You can see somebody already kind of did some red underlining in some of these things. At the beginning it says that geothermal piping shall be manufactured from virgin HDPE resin. That's a good thing, but by the way, you get that automatically because all pressure pipe is automatically made in virgin resin. There is no recycled product going in any kind of pressure pipe in North America. It's not allowed in the standards. So you don't actually have to specify that.
Excuse me?
Yes?
Is it allowed to their own waste in the pipe production to add like
Yes.
10% or something like that?
Yes, that's called reworked material. So you're allowed to use reworked material from your own Like if you extrude some pipe and the dimensions aren't right, you can chop it up and melt it down and re-extrude it again, as long as it hasn't left the plant. But we're not using milk jugs in anybody's pressure pipe. Milk jugs are widely used in drainage pipes, non-pressure pipes, but not in this. And down below, this is where it gets really confusing, especially for the Canadians. It says the piping shall have a nominal diameter of 32 millimeter or 1.25 inches. Well, even in the Canadian standards, there is no 32 millimeter pipe. Although Canada is mostly a metric system international country, when it comes to pipe standards, just like 2x4s, in Canada, 2x4 is called a 50 millimeter by 100 millimeter wood stud. It's the exact same 2x4 stud that we use in the United States. And even in the CSA Canadian standards, it doesn't even call it a 32 millimeter pipe. It calls it a 1 1/4 pipe or a 2-inch pipe or something like that. So this could be really confusing though, because the only way you're going to get a 32 millimeter pipe is if you bring it in from Europe, because that's where they make metric pipes over there, or South America or something. So that's kind of confusing. Down below it talks about the pressure rating. The metric conversion is not right. And then it also says the pressure rating applies to the resin. If you can read point 8, it says you must use a resin that has a given pressure rating. There is no pressure rating for the resin because the resin doesn't know how thick you're going to make the wall of the pipe. The pressure rating depends on how thick the wall of the pipe is, not the strength of the material directly. So the resin itself does not have a pressure rating. So that was good intentions, but that was wrong. This is also part of the same specification from the same engineer, and I apologize, the screen's not giant, so it's hard to read back there. The first thing underlined says, all distribution header pipes shall be 4710, but again, they're specifying metric dimension pipes, 50 millimeter and 75 millimeter. Nobody's making those in North America, so if you really wanted a 50 millimeter pipe, somebody's going to have to be importing that from Europe in that case. Right, that's right, and special fittings and everything else, and then you have to adapt it somehow to the rest of the inch-size pipe. And then on the bottom it says virgin HDPE resin with a cell class of 345564 or 345434. Those are really low-grade products used for conduit, non-pressure pipe used for fiber optic conduit, and they do not meet the standards that are listed in here. So the page is conflicting with itself. This is example number 3 right here. Again, they're referring to metric pipe, probably a spec from the same company. They're mixing in material types and classifications that don't match with PE 4710. And then down below, if you can read this, it says, provide a certificate of origin of the pipe pigment and resin formulation from the pipe manufacturer. The pipe manufacturer, they don't want to tell you where they actually got their resin and their pigment. That's kind of part of their proprietary information. The certifier knows that, but they don't tell that to the public because they don't want you to know where they're buying their resin. So you can ask for that. And then it also says the certificate will have a CSA stamp. CSA doesn't stamp certificates for companies. You can go online to the CSA website and find companies that have a product listed to the CSA standard, but you're not going to find the resin type or the pigment type. Again, because that's kind of proprietary information. So those were 3 examples of specifications that were written poorly. And I don't know if you caught any other glitches or flaws in those examples that I showed. But hopefully every one of those examples shows why you actually need to write a specification that is good, clear, up-to-date language. Otherwise, if I was the pipe supplier or the contractor in any one of those projects, I would have no idea what kind of pipe to actually supply. And I'd just be kind of guessing, because there's a lot of pipes. Well, for some of that language, no pipe will meet these requirements. So who knows what you're going to get. You're probably going to get a bunch of phone calls asking you to change the spec, quite honestly. Hopefully that would be the outcome there. All right, so that was the problem. Now let me introduce the solution. So we actually do have a cure for this. And it's called PPI Model Specification MS7. As I said in the beginning, one of the things that our organization does is we work with all the members of our organization to publish these model specifications. And our organization membership actually also includes the standards developers like CSA is part of our organization, and also the certifiers, IAPMO, ICC, NSF. representatives of those organizations are also part of the Plastics Pipe Institute. So we work with everybody involved with all aspects of the pipe industry to come up with good publications that are technically valid. Be great. So we're going to show you how to get access to this. It's a free download on our website, no charge at all. So when you download it, you download a PDF version. If you want a Word version, just email me and I'll just email you over the Word language if that's easier to copy and paste from. So the one on the left is the one in geothermal piping that we're going to be focusing on. The one on the right is for a model spec for polypropylene piping for any kind of application. But just to show you, we have kind of a family of specifications. So for the one for geothermal piping, again, it's called MS7, and it basically has 4 sections. The general section, ground loop piping, the products, the installation, and then the indoor piping is section 4. So there's the table of contents of it that lays out those 4 sections. It's nicely organized. The first part gives you a bunch of definitions. If you hear people talk about U-bend fitting, U-bend assembly, U-bend pipe, whatever, and you're wondering what is really the term that we should be using for this, you can use our definitions. And in a lot of cases, our definitions are very close to the definitions that you would find in a CSA standard or an IATMO code or an ICC code or something like that. So these are kind of like industry terminology, generic. There's a whole section here in reference sections. So if somebody talks about ASTM D3035 and you're wondering what the heck is D3035 all about, you can actually find it on the list right here. Oh, there it is, ASTM D3035, and there's the full name of it. So that's all found in there. Section 2 then is all about the piping. And it actually gives you 3 sections for piping. And I didn't really introduce the other piping materials very much before. It has a section on HDPE. It also has a section on PEX and a section on PERT, polyethylene of raised temperature resistance. Like I said at the beginning, 99% of all the ground loop piping out there in North America is HDPE because it does the job fine, it works, it's resistant, it's okay. But sometimes we get involved with geothermal systems that need to withstand higher temperature water than what HDPE can withstand. The maximum temperature exposure for HDPE is 140 degrees, but even at 140 degrees, the actual pressure capability is about 60% less of what it is at room temperature, because it's a thermoplastic, and as you heat it up, you soften it, it's not as strong. So if you get involved with higher temperature geothermal systems, maybe you've got some solar thermal that's collecting solar thermal energy, and you want to push that heat into the ground, charge up the battery, and then withdraw from the battery later on, you might need a higher temperature material. That's where PERT and PEX come in. Those are both pressure rated for 180 degree constant operation. They're more expensive, so most people aren't using them, but they are options that exist. So if you're writing the specification, though, you as the engineer should decide which of these materials is acceptable. If you want to allow the option for all 3, that's okay. But just know that most people are going to supply HDPE because it's the least expensive of those 3 options. Now, if we take a close look at the HDPE section, you're going to find some language that is very familiar. It's referring to CSA standards and ASTM standards, the same standards that we saw in the codes before. These are the proper standards, and that's the way we refer to the pipes in terms of their minimum capability is through those standards. So that's the very first requirement that you'll see. And then the next thing you'll see under material, letter B is for material, it says it shall be PE 4710. An old version of this used to say PE 3608, but nowadays, like I said, there's not really anybody even making any pipe in North America that's not PE 4710, so why not specify the best material for your HDPE ground loop piping? So that's what we've got in there. The next letter is requiring a listing with the Plastics Pipe Institute. So our organization provides third-party listings for the long-term pressure ratings of pipes, and those are found on a standard called PPI Tier 4. The next part down requires that the pipe be certified to the requirements of NSF 358. That's the one that also requires the compatibility test for the different types of glycol. The next letter down requires certification to NSF 61. That's the standard that requires the pipe to be tested and proven to be safe for contact with drinking water. In other words, if you put it through an aquifer or a lake or a river, you're not going to contaminate that water with the pipe in any way. And then the final one refers to the minimum wall thickness of the pipe and pressure rating of the pipe. being in compliance with Table 1. Table 1 is within the standard, and I'll show you this in a second. But before I move on, one thing to point out at the beginning, it says the specifier should not list all 3 ASTM standards. Anybody know why? What would be the problem if I said it's okay to meet ASTM D2737, D3035, or F714? The same pipe can't meet all 3, because 2 of those standards are for pipe dimensions, one of those standards is for tubing dimensions. So a pipe can't be a tubing, and a tubing can't be a pipe from a specification point, because the dimensions are actually different. The Table 1 that I refer to, though, this is where it specifies the minimum wall thickness of the pipe using a term called SDR, which stands for Standard Dimension Ratio. And let me jump forward, then I'll come back. Standard Dimension Ratio is this right here. It's the ratio of the wall thickness of the pipe to the outside diameter. So it's basically OD divided by T in pipe terminology. And the way that equation works, it's a very simple equation, the way that ratio works, standard dimension ratio, is the higher the number, the thinner the wall. So an SDR 21 pipe has a much thinner wall and a lower pressure rating than an SDR 11 pipe. It's just how the math works because you're dividing one by the other. So the way the Table 1 works back in our model spec is we say for pipes going into vertical installations, the maximum number of the SDR you're allowed to use, it used to be SDR 11, and now because the pipe requirements are all meeting PE 4710 requirements, it's a stronger, stiffer material, better resistance to slow crack growth, we can thin the wall out a little bit and allow SDR 13.5 pipes. So SDR 13.5 pipes have a slightly thinner wall than SDR 11 pipes, which means what?
It's cheaper.
Better heat transfer. Thinner wall is also more flexible, easier to uncoil, it's lighter weight, and basically when you buy polyethylene, you're buying it by the pound, so it's also going to be a little less expensive too. But the big technical advantage is better heat transfer because there's less pipe for the heat to transfer through. So this is a bit of a technical advantage here to allow the thinner wall pipe. Yep.
Is SDR 13.5 a common SDR ratio here in the United States?
Not yet, but it's going to be.
Because if you compare the weight of a probe in SDR 11 and 13.5, the price difference is minimal. It's, if you compare it to the total cost of drilling and all that, it's nothing. It gives you a little bit more of security. So in Europe, everything is in SDR 11.
Okay, and that's still the case here too.
It's still the case.
Yep, but the future standards, the new version of CSA C448 will allow the SDR 13.5. So it's an option.
And the pipe manufacturers will be happy about that because they have to change all the dimensions and everything.
They already have the dies, they can already make it. They'd rather sell a thicker wall pipe because then they're selling more weight. They're selling a more expensive pipe. So it's kind of a case where the specification may be a little bit ahead of the common market practice. So great question. So anyway, that tells us in terms of how to write the language on the pipe. That kind of tells you how to write the language on the pipe. Now it is up to the engineer then to also decide what pressure rating do I need for these pipes. And the engineer should specify what SDR is acceptable. So still, the engineers today will be saying SDR 11, but as they adapt to this document and the new upcoming versions of the standards, they can move to SDR 13.5 if they want to. They don't have to. SDR 11 is better than SDR 13.5 from a strength and pressure standpoint, so they can do it that. On the pipe and tubing fittings, the fittings used for the pipe and tubing, here's the requirements in the standard there. Again, there's different standards that I mentioned before for the different types of fittings. And one of the things it says in here that's important is for the so-called U-bends, the U-turn fitting that gets connected to 2 pieces of pipe to make a U-bend assembly going down a borehole, those shall be factory fabricated. Pretty much everybody is doing that these days already. But what we don't want is guys out in the muddy trenches fusing their own U-bends together and then dropping them down the trench because there's a chance of potentially a fusion flaw. So to give you an idea of what a factory fabricated assembly looks like, this is a picture taken from a polyethylene pipe company's factory where they take 2 coils of pipe, the ends of them together here, they're going to face them off to make them flat and square. Here's the fitting over here, and then this is the electric heating iron that's going to be dropped in between, and it's all done in a big automated machine. So if you're doing automated factory fusion of the U-bend, you can imagine that that's probably better than something being done in a wet trench. So this is not a big ask. Everybody does this already. And then for the installation of the fittings, there's requirements there for the ASTM standards to follow there. And I'm almost done here. So that's kind of the details for the HDPE pipe. For PEX, there's similar language in here for PERT. It's organized in the same way, but the standards and some of the code requirements for PERT are different than they are for HDPE. And then similarly for PEX. If you do want to specify PEX, there is language in here for the PEX materials, PEX U-bends, PEX fittings. Here's a list of some different types of PEX fittings that exist that are approved for geothermal piping as well. So all of this language is in the standard. There's a special note under that table, which you can't read, but it clarifies the metric pipe thing. Basically, it says, don't specify 25 millimeter pipe, because there is no 25 millimeter pipe in North America. In North America, all our piping is either pipe size, meaning it has the same outside diameter as iron pipe, or it's tube size, meaning it has the same outside diameter as copper tubing of the same nominal size. Nominal size means 1 or 2. So that's just a little bit of a detail on that there. There's a whole section on here on installation, how to put the pipe in the ground correctly, so the engineer can copy and paste this. There's a whole section in here in the bend radius, minimum bend radiuses, so you don't kink the pipe. The engineer can copy and paste this. There's a section in here on prevention of hydrostatic buckling or collapse, protecting the pipe against too much pressure inside or outside. There's a section on horizontal pipe installation. You can copy and paste that as well. And then a whole section here on field quality control, and then also on pressure testing, so that you have good language about a good pressure test method for the pipes installed in the ground. So again, you can copy and paste all that information. So it's a lot of detail. I'm not getting into all the detail here, but as you have an idea, there's a lot of great detail inside the specification. Yes?
I have another question. Is it required to do a pressure testing after the installation of the probe on site?
It's generally not required, but it depends on the engineer. Some engineers will require that every pipe in the borehole be pressure tested before it's connected to the lateral headers. It's a good idea, but generally our standards here don't require that. But the engineer, the specifier writing the standard for a project could certainly say to do that, because sometimes it's a different contractor. One contractor puts the pipe in the ground, and another contractor comes back and does all the lateral connections. So you want the guy putting the pipe in the ground to leave good pipe behind before it gets left over and turned over to somebody else. And then finally, there's a section here in the indoor piping, which now we also include the polypropylene pipe, which is a rigid pipe, which is perfectly suitable to be used for indoor piping. Just on the comment of, again, pipe size versus tubing size, this is just an illustration. If it's CTS1 tubing, that's the actual outside diameter. If it's IPS1 pipe, it's about 15% larger. So if you're specifying 1-inch PEX or 1-inch PE, make sure you also specify if it's IPS or NPS1 or CTS1 to make sure you get the right product. And then, by the way, this is our very first edition of a model spec for geothermal piping. So right in the very second page under the cover here, there's language in here that says, please send suggestions for improvements to this specification to PPI or any of our other publications. And there's our contact information right there. So this was the first one out of the gate. We want feedback. Download it for free. Take a look at it. Use it. If there's something in there that you think should be updated or revised in some way, let us know. And we have methods for changing the documents every few years after they're published. Before you go, there's just one more thing I want to show you, and I know the time is 2:30, so this is my last minute. We also have a fantastic pipe calculator for free on our website. Just go to plasticpipecalculator.com, and it includes all the geothermal pipe materials, plus plumbing materials, radiant heating materials, district energy pipe materials, all the different fluid types you might want to use, including methanol, ethanol, brine, water, and you can do pressure drop calculations, pipe volume weight calculations, any other kind of calculation you want to know about the fluid in the pipe itself in this calculator for free. So You would select the pipe type here, HDPE, and if you're doing a pressure drop calculation or something like that, you enter in your flow requirements and your temperature, your fluid type, hit the calculate button, and then it'll tell you what the pressure drop is in PSI or feet of water and what the velocity of the fluid would be in the pipe at that flow rate. So it's a great tool that's available for free. And with that, up to a screeching halt, we got through everything. Thank you for staying here and for staying awake. I know it's hot and everything else, but I'm willing to stay along for any questions. My contact information is on the bottom. If you have any questions, feel free to email me afterwards. And thank you for your time.